Hey everyone, and welcome to this explainer. Today we're tackling what is arguably the ultimate automotive engineering challenge. For over a century now, car manufacturers and engineers have been staring down one massive, persistent hurdle. The question is, how exactly do you get significantly more power out of an engine without just making the engine physically massive, incredibly heavy, and frankly, wildly inefficient? It's an attention-grabbing question, right? I mean, how do we actually squeeze more power and get better fuel efficiency without building a giant gas-guzzling engine block? Well, the brilliant and honestly super elegant solution to this engineering paradox isn't found by just slapping on more cylinders. The secret is actually hiding right beneath the car, waiting inside the exhaust pipe, and it utilizes energy that would otherwise literally just vanish into thin air. Okay, let's dive into this. What exactly is this magical device? At its core, a turbocharger is what we call a forced induction device. It's powered directly by the flow of exhaust gases, and its primary job is to drastically increase an internal combustion engine's overall efficiency and power output. So instead of just letting all that waste energy escape out the back of the car, a turbo captures it and puts it straight to work. Here is our roadmap for the explainer today. First up, we'll cover the need for boost. Then we'll break down exactly how a turbo works. After that, we'll look at the different types of turbochargers, weigh the advantages and disadvantages, and finally wrap things up with maintenance and common myths. All right, kicking things off with Section 1, the need for boost and why manufacturers absolutely love turbos. The true genius of a turbo really becomes obvious when you directly contrast it with a traditional, naturally aspirated engine. You see, a traditional engine relies completely on standard atmospheric pressure to basically pull air into the combustion chamber. It's like taking a deep breath on your own. If you want more power in a naturally aspirated engine, you physically need larger cylinders, a larger engine displacement to pull in more of that air. But a turbocharged engine, it completely rewrites the rulebook. It literally forces compressed air into those cylinders. What this means is you can take a much smaller, lighter engine and force it to yield the exact same or sometimes even way more power than a massive naturally aspirated V8. Let's move to Section 2, how a turbo works. We're going to break down the anatomy and physiology here. So let's actually follow the literal path of the exhaust and air to visually track this whole process. In Step 1, hot exhaust gases exit the engine right after combustion. Normally, these just shoot straight out the tailpipe, right? But in Step 2, we route those exact gases to hit a turbine wheel, spinning it at unbelievably high speeds. Now, Step 3 is the real stroke of genius. That turbine wheel is physically connected by a shaft to a compressor wheel. So when the exhaust spins the turbine, the compressor spins right along with it. In Step 4, this rapidly spinning compressor pulls in fresh outside air and heavily pressurizes it. Step 5 pushes that hot, pressurized air through an intercooler to chill it down. And finally, in Step 6, this perfectly cooled, highly dense air enters the engine for the combustion process, creating a significantly larger, far more powerful explosion. So we have all this highly compressed air, but there's a big problem: heat. How do we solve it? Compressing air naturally generates massive amounts of heat, and as we know, hot air expands. Expanded air just isn't dense, meaning it doesn't contain nearly enough oxygen for optimal combustion. The fix? The intercooler. It essentially acts like a giant radiator for the air, chilling it down so the oxygen molecules pack tightly together. Cooling it makes it dense, highly combustible, and absolutely primed to make massive power. Which brings us to Section 3, types of turbochargers. Because as we're about to see, one size definitely does not fit all. Engineers have developed a bunch of variations to suit completely different types of vehicles. First up is the single turbo. This is your basic, super cost-effective setup designed to give a solid boost to smaller engines. Next, we've got the twin turbo setup, which, you guessed it, uses two turbos. Often, one is small, so it spools up quickly at low RPMs, and the other is larger to deliver massive power once you hit high RPMs. Then there's the twin-scroll turbo. This is an ingenious design that actually divides the engine's exhaust pulses inside the manifold so they don't interfere with each other, allowing the turbine to spool up much faster. Fourth is the variable geometry turbo, or VGT. This one has tiny internal vanes that continuously change their angle to match the exhaust flow, providing optimal power at practically any RPM. And finally, the cutting-edge electric turbo. This uses a literal electric motor to instantly spin the compressor wheel before the exhaust gases even arrive, totally eliminating any waiting time for that power to hit. All right, Section 4, advantages and disadvantages. Let's dig into the engineering trade-offs. Now, what's really interesting about this slide is seeing how every brilliant engineering solution comes with trade-offs. The benefits are undeniably massive. You get significantly more power, you achieve better overall fuel efficiency because the engine itself is smaller, and you get lighter cars that just handle better. Plus, interestingly enough, you get much better high-altitude performance because the turbo just keeps forcing air in, even when that mountain air gets incredibly thin. But we have to deal with the cons too. We get turbo lag, which is a delay in power. There's extreme heat generation that puts a ton of stress on the engine bay. These engines also require much stricter maintenance routines from you, the owner. And if neglected, well, you're looking at potential long-term reliability issues compared to a much simpler non-turbo engine. Let's actually pause and define that most famous drawback explicitly: turbo lag. This is simply that noticeable and sometimes pretty frustrating delay between the exact moment you mash your foot on the accelerator and the moment you actually feel the surge of engine power. It happens for one simple reason. It physically takes time for the engine to create enough exhaust gases to spool up that turbine wheel to its proper operating speed. Shifting gears into our final section, Section 5, Maintenance and Common Myths. It's time for some fact versus fiction in the real world. Okay, let's start by totally busting some incredibly common myths that are always floating around out there. Myth number 1, turbos are only for high-performance race cars. Absolutely false. Today, manufacturers are putting turbos in basic economy hatchbacks and family SUVs, mostly just to meet super strict efficiency and emission standards, not to go racing. Myth 2, turbos always ruin engine reliability. Again, completely false. Modern turbos are remarkably well engineered. They really only ruin reliability if they are severely neglected by the owner. And myth 3, turbocharged engines waste more fuel than normal engines. Actually, the exact opposite is true. A small, turbocharged four-cylinder making 300 horsepower is going to be significantly more fuel efficient for your daily commute than a massive, heavy V8 engine making that exact same 300 horsepower. So the crucial point here is how you treat the engine. If you take care of the heat and lubrication, the turbo is going to last. Here is the real-world maintenance you absolutely must follow. First, perform strictly scheduled oil changes. Your turbo is spinning at hundreds of thousands of RPMs. Clean oil is quite literally its lifeblood. Second, let the engine warm up properly before you decide to drive aggressively. Cold, thick oil just doesn't protect those turbo bearings well at all. Third, after a really hard drive, let the engine idle for just a minute or so to cool down before you shut the key off. This keeps fresh oil circulating so the residual heat doesn't just sit there and cook the stagnant oil inside the turbo. And finally, always use the manufacturer-recommended high-quality fuel to prevent engine knock. And that wraps up our deep dive into the world of forced induction. Turbos truly are a modern marvel of doing more with less. But it does leave us with a pretty fascinating question to ponder. As electric turbochargers instantly eliminate lag entirely, and emissions laws get tighter and tighter every year, will the traditional, massive, naturally aspirated engine soon disappear from our roads for good? Let me know your thoughts down in the comments. And hey, tell us what complex automotive engineering topic we should demystify in our next explainer. Thanks for joining us, and we'll catch you next time.